You'll do it, okay. Okay, so the plan for today is we'll talk about divide and conquer algorithms for sorting, for median finding, and for matrix multiplication. Now, in sorting, the divide and conquer algorithm, the classic algorithm is merge sort, which you've already seen in 61B. And then I believe you just did a review of that in the discussion section. So what I'll do is I'll talk about something related. Okay, so I'll talk about a related problem, and then we'll go through and think about how we solve it using divide and conquer. All right, so let's talk about merge sort. So first, let me just do a 1-minute review of merge sort. So what's merge sort? It's you're trying to sort an array of numbers A1 through n, and you want it in increasing order. So you want A1 less than or equal to A2 less than or equal to n. Okay, so we want to reorder the elements so that we get this condition. All right, so how does merge sort look? Well, what you do is you merge two sorted lists. So you divide the list into two parts. So you first run merge sort on A1 through n over 2. And you also run merge sort on A n over 2 plus 1 through n. And I'm assuming n is even, so all this is okay. And then once you get back these sorted lists of n over 2 elements, then you merge them together. And merging takes linear time. So you get back these two lists. This is n over 2. There's another list of n over 2. Each of these is sorted. And now what you want to do is you want to merge them into one sorted list. So you just walk along the one list and along the second list. And you just keep keep pulling elements off according to which order they should go in. Okay, so the running time is just t of n is 2 times t of n over 2 plus order n. And now you can sort of see this is the case where t of n is order n log n, either by explicitly working out the recursion tree or by working through the master theorem. Okay, so that's merge sort. Now what we want to do is something slightly different. What we'd like to do is solve this problem of what we want to figure out the number of inversions. Okay, so what do we mean by an inversion? So we have an inversion if I is less than j, but a of I is greater than a of j. Okay, so if you have an array which looks like this, if a1 was 5, 1, 3, 2, 4. Okay, so then we can sort of figure out how many inversions are there. Well, 5 should not be before any of these elements. So there's 1, 2, 3, 4. So 5 is involved in 4 inversions. Okay, so let me just write down below each element how many inversions it's involved in. This is involved in 4. 1, well, now we can say, well, 1 is involved in how many inversions moving forward from here? Well, 1 is involved in no more inversions. 3 is involved in 1 more inversion. 2 is involved in no more inversion. Okay, so the total number of inversions here is equal to 5. Does everyone see what I mean? Okay, so what I'm saying is, here are the inversions. This, 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 and this. Okay, I'm claiming other than these, every other pair is in the correct order. In general, the number of inversions could be as many as n choose 2, right? So the obvious algorithm, which would be to look at every pair and to see whether they are out of order, would just take n squared time. Okay, so how can we do faster? So before talking about that, let me just say that these number of inversions are interesting for more than one reason. One is it sort of determines the complexity of this very simple-minded algorithm called bubble sort, which you may have seen. But the other reason for thinking about number of inversions is that, if you're given an ordering of two different lists, so if you are sort of thinking about how do you rank all your favorite basketball players, and your friend has a different ranking on all the different basketball players, and you want to say, how similar are your lists, right? Well, one way to compare, to put a number on it, is to look at your list and to say, how many inversions are there between these two lists? That's a crude measure of how differently you value the same the same set of people or items. So it's an interesting measure to have. Okay, so now how would we actually come up with an algorithm for this? So one way you might think about doing this is by divide and conquer. And so what I want to do here is I want to walk you through how one thinks about divide and conquer, and how one thinks about it in the context of just a problem like this. Okay, so let's move to the next page, and let's say we are looking for number of inversions, which is, there's an inversion when I is less than j, but ai is greater than aj. Okay, so how would we do this using divide and conquer? So here's an idea. So what we could do is, of course, we could take our list. This is A, and we could divide it into two parts. And then we could, of course, when we divide it into two pieces, we recursively call the left part and the right part. And we don't have to worry about this, because magically the recursion is going to tell us how many inversions are there on the left half, how many inversions are there on the right half. But now, how do we figure out the total number of inversions? So if you want the total number of inversions, what we are missing is the number of ij pairs where I is here, sorry, where we have element number I here and element number j there, but this is bigger than that. So if this was 10, this was 3, well, that's an inversion. So we want to count. So these are the kinds of inversions we are missing when we solve the problem recursively, and we figure out what's the inversions on the left half in this part of the array, and what's the inversions in that part of the array. So how do we figure out all of these inversions very quickly? Okay. So this is where it would be helpful to us if in our recursive calls, not only did we figure out the number of inversions on the left and the right, but we also sorted those lists. So what we'd like is that our recursive calls do two things. One, it sorts, and two, it figures out number of inversions. Right? Okay, because now, if we are done with that, now we are off to the races. So here let me show you why. So let's say that our left sublist was sorted, and it was 1, 3, 5, 7, 9. And our right sublist was sorted, and it was 2, 4, 6, 8, 10. Okay. So now, what would we do next? Well, what we would do is we do sort of the same thing that we do when we merge. So we would sort of start with this first element and figure out where it fits in. And it fits in out here, right? Meaning that it contributes to no inversion at all. Then we figure out where the second element fits in. Well, it fits in out here, right? So 1 fits in out here, 3 fits in out there. And therefore, we can read off that it contributes to only one inversion. We figure out where 5 fits in. 5 fits in over here. So we can read off that, so this gives us number of inversions. Oops. So this contributes 0, that contributes 1, that contributes 2. 7 fits in right here. And so it contributes 1, 2, 3 to the number of inversions. And 9 fits in right here, so it contributes 4. And so if you want to count the number of inversions, we just add up 0 plus 1 plus 2 plus 3 plus 4. So we'd get 10 inversions out here. Okay. So I claim that this would be great if now what we have is an algorithm where we'd get this kind of running time. So I'll write out the algorithm in a moment, but I'm claiming that what we are aiming for is an algorithm where we split the problem of size n into 2 subproblems of size n over 2. And then to compute the number of inversions that happen between the 2 sublists, it only takes us linear time because it's just like merging. And so this would also be T of n equal to order n log n. Okay, so is this clear? So now how would we actually do this? Well, so what we are going to do is we start off with our list A. Okay, so we start with list A 1 through n. We recursively, so our recursive calls to this procedure for figuring out the number of inversions would give us back, each of these recursive calls will give us back 2 things. So the first recursive call will give us back an array B of 1 through n over 2, the first half, but sorted, and as well as a number, K1. This is the number of inversions there are in that sublist. Then we call this subroutine on the second half. That gives us back C of 1 through n over 2, another sorted list, and a number K2, which is a number of inversions. Now what we need to do is we need to take these 2 arrays and we need to figure out the number of inversions between the 2. Okay, so how do we do this? So what we are going to do is for I equal to 1 to n over 2, what we want to do is we want to locate the ith item. We want to locate bi in the C array. So we call this, we call a procedure locate, which takes as input the array C. It takes the index J, and it takes as the input B of I. So what are these three things? So this is the array B. This is the array C. So what it does is, if we are currently processing the element 5, what it takes is the index j. So right here, j is equal to 2. It says the current array that we are looking at is so far we've processed this far in the array B. And if you look at the elements 1 and 3, they fit in here and here, and the rest of the array is still unprocessed. So j is this index. It says j. We still have to process the array C all the way from the second element onwards to n over 2. Okay, so now so at this point, B of I in our example would be equal to 5. And so we'd go ahead and locate it, and it would give us back a new index. So the new index it would give us back was j equal to 3 in this case, right? Okay, so that's the procedure. All we are doing is walking along. So we first locate 1 in this array. So we just walk along from left to right in this array. We locate 1 in there, and then wherever we stopped off, we start from there and locate 3, because it's in sorted order. We can just go left to right. And then what we do is, each time we do this, the number of inversions, we set it to number of inversions plus j minus 1, right? It's everything to the left, which is an inversion. Okay, and once we are done with all this, we can just output the number of inversions. Okay, so that's an algorithm that takes n log n steps. Okay, so let me just say a couple of words about this. So how would you prove correctness? So to prove correctness, you would obviously do this by induction on n. And what would you prove by induction on n? Well, there are two things we are proving about this algorithm. One, that it sorts. Two, that it computes the number of inversions. Okay, so why does it sort? Well, because it sorts each half by the induction hypothesis. And second, because merge works. Why does it compute the number of inversions? Well, because it computes them for each half by the induction hypothesis, and then it computes them across the cut by the fact that locate works well. Okay, so that's how you would actually do a proof of correctness if you wanted to do it formally. And in terms of running time analysis, as we said already, because locate is just walking left to right across this array, it takes order n time. And so T of n is 2T of n over 2 plus order n, which is order n log. Okay, so let's see. Maybe this is a good time to stop and see if there are any questions.
Yeah, Professor.
Yes.
So I was wondering why the overhead per recursive call is O of n, because it seems like locate would be linear, and we're iterating from I equals 1 to n over 2. Okay,
so here's the point. We are iterating I equal to 1 through n over 2, but what we are doing is we are walking across. Locate is walking across this array, right? So it starts from the left end, and it processes the first element, so it walks across some distance. And the next time when we call it on the next element, it doesn't start from the beginning all over again. It starts from where it stopped off, because it knows that the new element is, you know, we are picking these elements off one at a time from we are picking these elements off one at a time from a sorted array, right? So wherever we left off with the first element, when we process the second element, we don't have to go across all the way here. We know that element is only going to fit in somewhere to the right. So it just starts from where it stopped and keeps moving right. And so the second time it might stop here. And then when we process the third element, it keeps walking from there until it stops. So the total amount of time taken to process all the elements is linear.
I see.
Okay.
Thank you.
Hi,
Any more
Professor.
questions? Yes.
Can you help me understand how you counted the number of inversions again? I couldn't really quite understand before.
Okay, so here's how you count the number of inversions. So let's say that you locate an element. So say I locate an element and it fits in exactly into this gap over here, right? So now what I know is that it's larger than all of these elements to the left, right? Meaning those are all the inversions. So if I know the index where I stopped, then I know, you know, if I stopped at a certain index, then I know everything to the left is an inversion. So I can just that's why I added to the number of inversions j minus 1. It's, you know, it's the number of you know, it's a right. Okay.
So when it's located at that location, all the other elements on the left are bigger than the one at the locate. Is that why there's an inversion?
Oh, sorry. So what am I doing? So what I'm saying is, you know, suppose we put in located the element 5. So 5 fits in over here, right? Now, it started from the left side in A, right? So it should have been smaller than everything on the right side. Yeah.
Right.
But in fact, it's larger than these first two elements. So that's the number of inversions we have that 5 is involved in.
Oh, I see.
Does that make sense?
Yes. Thank you.
Okay. Okay, good. Other questions?
Professor.
Yeah.
So if you're doing this step on every recursive call, isn't there any problems with overcounting?
Overcounting. Why is that?
Since we're like counting the
Okay,
inversions for two lists every time.
Okay, so here let me answer that. So what we are saying is the total number of inversions is the number of inversions involving two elements on the left side. So that would be right here in this subarray, right? So if I have a pair of elements that are inverted, either both elements are on the left side or both elements are on the right side. These will be caught in the recursive calls. Or one element is on the left and one element is on the right. This will be caught during this locate. Okay, so I'm counting everything exactly once.
Okay, and you're sorting the list using merge sort, right?
Yes.
Okay.
So in fact, you know, while doing locate, we are actually doing merge. We are just doing it one step at a time.
Okay, thank you so much.
Yeah, sure. Other questions? Okay, so now let's move on and let's talk about another topic, which is okay. So one thing I hope which is becoming clear is that divide and conquer is all about recursion, right? it's a way to understand recursion deeply, right? Because you use it in a deep way in divide and conquer. Okay, so now let's do one other thing about sorting, which is let's try to understand this question. Can we do better? Okay, could we possibly do, we said the algorithm is order n log n, so can we do better than n log n? And so to understand this, we're going to, again, do an abstraction, right? Remember, algorithms is about abstraction. So the abstraction that we are going to bring in is that we are going to acknowledge that all the algorithms we are looking at involve comparisons. So we'll just think of each element of the array, not as a number, we'll just think of it as sort of a hidden element where we don't even get to look at the element. The only way we get to probe this element is by doing a comparison, right? So we think of this array now, and this array consists of 1 through n. There are n elements, but these are hidden behind. There's some. They're all hidden from us. And the only way we can never query what's A1, what's A2, what's A3, that these are numbers. We'll just forget about all that and we'll say, look, the only way we can ever get any information about these is we can say, is A1 greater than A5? And the answer is going to be yes or no, right? So this is the only way we've ever used our list of numbers in all the sorting algorithms that we've seen. Okay, so now here's another thing that we can do now. Now that we make this abstraction, we can say any sorting algorithm looks like this. It starts off by making a comparison like this. Is A1 bigger than A2? Question mark. And the answer is either no or yes. Right? And then we ask, is A1 bigger than A3? Question mark. Again, the answer is either no or yes. And similarly out here, we could ask, is A2 bigger than A3? Question mark. Again, the answer is either no or yes. Okay. And so now we could stop here, and then we could ask, how well did we sort our array, right? So suppose that we had, these were possibilities for the array. It was either 1, 2, 3, or 1, 3, 2, or 2, 1, 3, or 2, 3, 1, or 3, 1, 2, or 3, 2, 1, right? There are 6 possibilities. One is, the first one is the smallest, second, third, or it's biggest, smaller, smaller, right? That's there are only 6 ways that you can sort out this array. And so we can ask, well, how does it all work out? So if we look at it, is A1 bigger than A2? And it turns out that there are exactly 3 of these where A1 is bigger than A2. And there are 3 where A2 is bigger than A1, right? So if we think of, one way we could think of this is that we are sort of inserting one of these 6, permutations in at the top of this tree. And it's, and the permutation sort of percolates down. Each one either goes down left or right and so on. And so we can ask, where do they end up? Well, it turns out these 3 will end up on the left side. And then when we ask, is A1 bigger than A3? Then these 2, 3, 1, 2, and 3, 2, 1 will end up here. Yes, A1 is bigger than A3, and 2, 1, 3 will end up here. A1 is smaller than, smaller than A3, yeah. And same thing over here. You know, two of the remaining will end up in one of these, and one will end up in the other one. So now, is this a good sorting algorithm? What we've just written out? Well, the answer is no, because at the end of this algorithm, we could not tell the difference between these two permutations. So as far as this algorithm was concerned, it cannot tell whether the second element is smaller than the third element or it's bigger than the third element. And so it's left them sort of unsorted in some case, right? And so it's a necessary condition for this algorithm to be good for every leaf to contain exactly one permutation. Okay, so let me sort of back up and say what we are doing here. We are saying, first we said we are going to be in this comparison model. All we can do is comparisons. Then we said any algorithm in this comparison model can be written as a tree. And then any execution of this algorithm can be written as a path from the root to a leaf of the tree. And furthermore, we said for this algorithm to be correct, every leaf must have at most one permutation in it, right? Because if it has two, then it's getting confused. So therefore, the number of leaves must be at least n factorial. That's the number of permutations on n elements. And therefore, the height of the tree. Remember, each path from the root to the leaf is an execution, is a particular run of the algorithm. So if you look at the height of the tree, that tells us what's the maximum time this algorithm can take, right? So the height of this tree is equal to the running time. In the worst case, is going to be log of n factorial, right? But what's n factorial? Well, n factorial, which is about which is n log n. Another way you can say this is, well, n factorial is certainly greater than n over 2 to the n over 2, right? Because it's n factorial is 1 times 2 times 3 times so on up to n. And so if you look at the last n over 2 terms, then each of them is larger than n over 2, and there are at least n over 2 of them. So n factorial is larger than this, and therefore log of n factorial is larger than n over 2 log n over 2, which is like n log, right? So this tells us we cannot do better. Okay, so maybe shall we talk and stop and take some questions now? Yeah.
Sir.
Hello?
Yes. Yeah.
I had a question about why the number of leaves are greater than n factorial in this case.
Well, it's at least, the number of permutations on n elements is n factorials, and each of these permutations must occupy its own leaf.
Yeah.
So the number of leaves must be at least as many as the number of distinct permutations.
Professor?
Okay, right? Yes.
I was just wondering, why is the height of tree equal to running time?
Okay. Well, what does a tree represent? So, what the tree represents is every possible, so it represents every possible execution of this algorithm. So it's saying, look, right in the beginning, we are going to ask this question, is A1 bigger than A2? And depending upon the input, depending upon which array you're trying to sort, you'll either go left or right. Yes? And then depending upon which way you went, you ask another question and then you go either left or right. So an execution of this algorithm on a particular input. So you fix an array and how does it go down? So, if you have your input 2, 1, 3, then you ask, is A1 bigger than A2? No. So you'll go down this path. Now, then you'll ask, is A1 bigger than A3? No. Then you'll go down this path. So that's, you fix your input and you'll choose a path down the tree from the root to a leaf, right? And so now, it could be that some of these paths are very short, but to find the running time of the algorithm, we have to say, what's the worst case running time? If you look for the longest path from root to leaf and you say, there's some input on which I can make it go for a very long time. So that's the height of the tree, right? That's the running time of the algorithm.
Professor?
Yes.
So for the very last worst case scenario, what did you put between the two ends?
Very last worst case scenario. Where do you see
At
this?
the very bottom right of the screen.
This one?
Yeah. Would you
This
put?
or here?
No. What you said earlier, what you pointed at earlier.
Oh, this omega?
No. Between the two ends.
Between the two ends. This is n over e to the power of n?
After that, like it says omega, and then there's n, then something.
N log n. N log n.
Okay. I didn't know that. Okay, thank you.
Yeah. Okay. All right.
Professor, yesterday
Yes.
we were talking about like some trees, and then you said running time is dominated by the number of trees, like number of like.
No, that had to do with the recurrences, and when we are saying that was in a different context when we were writing T of n equal to A times T of n over B, etc. So it was solving the general formula, right? Is that what you mean?
Yeah.
Yeah, that was a different context. That tree was different from this tree, right? That tree represented the analysis of a divide and conquer algorithm. And it said, how many levels of recursion do we have, right? As we do this divide and conquer. This tree is different. We are just saying, we are working in this model, the comparison model, and we are saying, what does an algorithm look like? Right? An algorithm looks like a tree in this model, where the interpretation is that a run of the algorithm is a path from the root to the leaf. Okay.
Umesh, there's a question by Michael Kortkov. He's saying, are we proving that finding the number of inversion is n log n or sorting is n log n?
I'm sorry. Oh, oh, sorry. Okay. Can we do better? So this was in terms of sorting. Okay. So we are saying to sort, you have to take at least n log n time. Good. Thanks for asking the question. Right. So here what I went back to is saying, if you were just sorting n elements, it takes n log n steps. And then I think I went over this very fast as we made the transition. So we're saying, can we do better while sorting? So merge sort gives us order n log n. And this tells us that we must take n log n, and therefore it's optimal up to constant factors.
When would there be more permutations than number of leaves? Or sorry, more leaves than permutations?
When would there be more leaves than number of permutations? So for example, what I could do is, after going down here, I could again do a comparison. Is A1 bigger than A2? Question mark. And then, the answer could be no or yes. Well, there's no permutation that can possibly go down this way, right? Because we already did A1 greater than A2. The answer was yes, so it can't change to no now. right? So there's going to be no permutation sitting here and only permutation sitting on this side. So you can sort of create these situations where you do something, you make the algorithm do something sort of silly and create more leaves than it needs to. Does it make sense?
Yeah, that makes sense. Thank you.
Okay.
Professor, there was for the previous part before we transition, could you show the proof of correctness, like where you explained that?
Okay, sure, yes. So I just said it was by induction on n, right?
I see, okay. So I guess that's fine, like for our homework too, if you say something like that.
No, so I said it was by induction on n, and then I explained how it went, but I didn't write it down. So what I said is, look, by induction on n, what we are going to claim is that it sorts and computes the number of inversions. So we have two sorted arrays now. We know the number of inversions within each one. And now what we have to do is we have to show that in the induction step, that in the rest of the algorithm, we sorted the larger list by actually merging it, but also in the process that we actually computed all the inversions where one element sat on one side and the other on the other side, right? And that we got all of these.
Okay, thank you so much.
Yeah, sure. Okay, so shall we move on and talk about finding medians? So in median finding, again, we are given a list of n elements, A1 through n. And now we want to find the middle element. We want to, if we were to sort it, so we want to find an element m such that half the elements are below it and half are above it, right? So if n was odd, then you can find exactly the median, and if n is even, then you find one of the two middle elements, right? Oh, okay, so we find the middle element in the sorted list. Okay, so one way you can do this is, of course, you can sort first and then pick out the middle element. But what we want to do is we want to do this faster. Okay? And so here's the way we plan to do this. Again, we want to do this by divide and conquer. So we take this list A. And now suppose that I could do the following. Suppose I could pick out some element between n over 4 and 3n over 4 in the sorted list. So let me think of this as the sorted list, which we don't have. But suppose I could reach in and pick out some element somewhere in here. Okay? Then what I can do is now I can compare each element of the list to this special element that I've picked out. This will take me n comparisons. And in the process, what I would know is how many are smaller and how many are larger, right? And whichever is the smaller set, I can discard it. And then, well, what I'm looking for is this middle element. So now I'd be left with this list, right? Not in the same order. This is my notional element. I'm pretending I have this sorted list just to understand what's going on. So suppose I had this magic way of picking an element somewhere between n over 4 and 3n over 4. Okay. Then what I could do is sieve every element past this one. So compare this element to every element in the list. So I'd be able to break my list into two pieces. Then I know that the larger of the two lists is certain to contain the median. But also, if if that larger list contains n over 2 plus k, if this has size n over 2 plus k, then I now know that I want to find the kth element from the bottom, the kth smallest element. So now, instead of looking for the median, I'm looking for the kth smallest element in this list, equal to median in original list. Okay, so now how do we solve this problem? Well, we just go back and check. You know, if I were looking for the kth smallest element to begin with, and if I could again follow exactly the procedure that I outlined. What I could do is, instead of looking for this middle element, I'm now looking for the kth smallest element in the list. What do I do if I have this magic way of picking some element between n over 4 and 3n over 4? Then I could compare this to every element in the list, break up the list into 2 pieces. And now it's not necessarily the bigger piece that's certain to contain it. It's, we just see, we have the smaller elements and the larger elements. We've divided the list into 2 pieces. And now we see if the list of the smaller elements is larger than k, then we know that in fact the kth smallest must be in this one. And if k is okay, so we have n1 and n2, right? So these lists are of size n1 and n2. If k is smaller than n1, then find kth smallest in this list. Let me call this list B, and this list C in B. If k is bigger than n1, then find k minus n1 smallest in C. Okay. So now, how long does this whole thing take? Well, what we are guaranteed is that n1 and n2 are both smaller than 3n over 4, right? Because we found we split the list at some point between n over 4 and 3n over 4. So what we'll get is a recurrence, which is T of n is at most T of 3n over 4 plus the time required to do this processing after picking this middle element. But all we are doing is comparing to every element in the list. So that's order n. And so what we're going to get this way is a geometric series, right? N, 3n over 4, 3 over 4 squared times n, and so on. So T of n is just big O of n. So you can do it this way, or you can read it off the master theorem, right? It's all the same. Okay, so all this is great, except we haven't answered the question: how do we find this middle element? Okay, so what we are going to do is we'll actually look, since that looks very much like the problem of finding the median or something like that, find something close to the median. Well, the way we are going to do this is we're actually going to pick the element at random. Okay, so to find this special element, we are going to just pick an element at random. And since we are looking for something between n over 4 and 3n over 4, half the elements will lead to success and half to failure. So we have a 50-50 chance of picking something in there. Okay. So now, here's a question. So does this analysis still hold if we have a 50-50 chance? What happens if we don't succeed? Okay, so what we'll actually show is that we'll just keep picking x at random, and the expected number of tries before we actually pick an x between n over 4 and 3n over 4 is exactly 2. So the expected amount of time that we'll take to get a problem of size at most 3n over 4 is still big O of n. And so if we let t of n instead be the expected time to find kth smallest in n element array. Okay, then I claim that this still satisfies the condition that it takes linear time, that the expected time is going to be linear. So this might not seem, just to make sure that this is crystal clear, let's just think about what the algorithm looks like and what the recursion looks like. So we start with our original problem, which is of size n. So let's say that this expected time, that the time it takes is n. I'm just going to pick a constant equal to 1 just for simplicity. Then how many subproblems do we get? Well, only one subproblem. So our tree has branching factor exactly 1. And at the next level, it takes at most 3/4 times n, right? The next level, it takes 3/4 squared times n. Here, I'm not using expected time. I'm saying, suppose we had a magic way of finding this element, right? Then this is how much time it would take, and so on. You get 3 over 4 cubed times n, and so on. So we get this geometric series, and so the total running time would be order n. But now, what I'm claiming is that if instead we use a randomized algorithm to try to pick this special element, then instead of time n, it's going to be the expected. So this, let's call this T1, T2, T3, T4. And so the total time is the sum of T sub I, and this is still order n, right? So now I'm claiming that the expected value of T1 is still, let's say, n, or let's say it's 2n. Expected value of T1, T2 is 2 times 3/4 n. Expected value of T3 is 2 times 3/4 squared times n, and so on. So now, what's the expected value of T, which is T1 plus T2 plus T, D, if the depth of the tree is D? Well, the expected value of a sum of random variables is just the sum of the expected values, right? So it's the expected value of T1 plus expected value of T2 plus ... And so that's this geometric series. So that's still order n. Okay. So I hope this makes it clear that we are throwing around expected values and probabilities, but it's all kosher, right? We are just saying, as long as we can show that the time required to pick one element and do all this processing is order n, then we are in good shape. Okay, so why is that the time required to do the processing for one step, for this one level of recursion, order n? Okay, so remember, we are picking this element at random. It has probability half of turning out right. Okay, so it's like we are flipping a coin. It's a fair coin. We are asking, how long do we have to wait before we get heads? The answer is 2. Okay. And so since each time it takes us linear time and n time, it'll take us 2n time. Okay, so here's the general fact. So suppose the probability of heads is p. So suppose w is the waiting time for a heads. So you flip the coin over and over again, and you say, you count how long it takes for you to get the first heads. Now, if you're lucky, w is going to be 1. If you're unlucky, it might be very large. But what's the expected number of steps? So here's how you compute it. So expected value of w is what? Well, with probability p, you'll get it right away. With probability 1 minus p, your first toss would be a tails. So you already weighted 1. But now that your first toss is a tails, remember your coin is completely memoryless. So given that you got a tails in the first toss, how long do you have to wait? You still have to wait w steps on average, right? So it's going to be 1 plus w. So p plus 1 over p is 1. And so then you get 1 minus p times w. Oops. Sorry. What I should have written here was expected value of w, right? And this should also be expected value of w, right? Okay, so then p times the expected value of w equal to 1. So expected value of w equal to 1 over p. So in our case, p is equal to half. So you have to wait for your expected waiting time is 2. Okay. Let me see how we are doing on time. Okay, so maybe I'll stop here for questions.
Professor?
Yes.
For the running time, how is it t of 3n over 4? Like, how did you get that part?
Okay, so here's what I'm saying. So look, we started with this list of length n, right? And then what we did was, if this is the sorted list, somewhere between n over 4 and 3n over 4, this was the element we picked. And then our new lists are this one and this one, right? But the kth largest element is either going to be on this side or it's going to be on that side. So we're going to throw one of these away and we're going to be left with only the other one. That's our recursive call. But how big is our recursive call? So regardless of whether it's this list or that list, it cannot be big. You know, what's the biggest it can be? Well, it can either go from here all the way to there, or it can go from here all the way to there. In either case, it's 3n over 4. That's the largest subproblem we could be handing off to our recursive call. Yeah? Does it make sense?
Yeah, so we are expecting whenever we partition, it would be in the range of 3n over 4.
Mm-hmm.
Okay, thank you.
And when do we determine when we find the median number? Like, when do we stop?
When do we stop? Well, certainly when we get down to an array of size 1, then we know that's the number we are looking for.
I believe the question was, how do you know that you got an element which is between n over 4 and 3n over 4?
Oh, sorry, that's what, okay. How do you know? Well, the point is you don't even have to know, right? Because we are just saying, we'll just keep running down, so in other words, let's suppose we have 2 algorithms in mind. One is our pretend algorithm where we are being stubborn and we'll say, look, every time we pick this element, if it's not between n over 4 and 3n over 4, we'll just throw it away and we won't use it, okay? The second is the algorithm that we'll actually run where we won't worry whether it's between n over 4 and 3n over 4. We'll just go ahead and use it, So I claim that the algorithm that we are actually using will only do better because we are processing more stuff. As long as here's what I mean. The pretend algorithm was the following. Every time we get a number which is not between n over 4 and 3n over 4, we charge ourselves n steps. We charge the algorithm n steps for the privilege of picking this number because it was supposed to actually compare every element to this one. So we'll charge you for that comparison anyway, but we won't process it and we'll throw the element away. So I'm claiming that that particular algorithm already, that's what we analyzed here. We said there we are going to 3n over 4 after order n steps. And so in the actual algorithm, we are only going to be doing better because we sometimes throw away more stuff. Okay.
Hi, Professor. I have a question.
Yeah.
If d1 equals to n, why is the expected value of d1 is 2n?
Why? Oh, expected value of t1. Sorry. This was the ideal case where we always know, where we can magically pick this element in the middle, right? This is the real case, right? So the ideal case doesn't exist. If we were doing the ideal thing, then it would take us only n steps. But in the real case, we are picking at random. It may work, it may not work. Then we pick at random again. It may work, it may not work, and so on. So it's actually going to take us longer. Moreover, we cannot even bound the time. We can only bound the expected time, right? So in the real case, it takes longer, and we don't have a guarantee. We just have a guarantee. We can only say that the expected time is at most 2n. Does that make sense?
Yes, thank you, Professor.
Okay.
So why do we want to find the median in such way? If we have already a sorted list, why don't we just take the ceiling or the floor of the length divided by 2?
Yeah, so if we had a sorted list, that's what we'd do. But the point is we are starting with an unsorted list. So this is an unsorted list. And we want to find the median in there. And then what I was doing was, we were pretending. Let's pretend we have a sorted list. This is just to understand our algorithm, right? So we said, let's pretend we had a sorted list. Now, okay, so this is for, how should I call it? This is for illustration or for explanation. So now we are saying, if we manage to pick an element somewhere here in the sorted list, then we would be in good shape because we are going to compare this element to every element in the unsorted list. And we can divide the unsorted list into 2 pieces, which are still unsorted. But then we can throw away one of these 2 pieces. Right? So that's our divide and conquer. Okay. Incidentally, I should point out something. So some of you asked me, is it always going to be the case that when we do our recursion, and run this recurrence relation to figure out the running time, that the maximum amount of time is spent at the leaves? That's right. And I sort of said, well, I'm hard pressed to think where it's in the first step. Well, here's your example where it's in the first step, right? So this is where most of the work is being done right up front. It's order n. And then, as you can see, you have this geometric series which sort of shrinks down to nothing by the end. Right? So the running time is dominated by the first term, not by the leaves, not equal. So in sorting, it was equal at every level. So you had log n levels of recursion, each took n time, so it was n log n. But now we finally have an instance where the first level takes the most time in the recursion. Okay, so let's go ahead and do the last topic, which is matrix multiplication. Okay, so we want to multiply two n by n matrices. So we are given two n by n matrices, x and y, and we want to figure out, so these are n by n. Okay. So if you want to compute the ijth entry, then the way you do that is you take the ith row of x and the jth column of y, and then you multiply the corresponding elements and then you add them together, right? So z right? So everyone happy with that? So now we want to use, so you can see the number of steps required to do this. There are n squared entries that you have to fill in, and the running time is order n per entry. There are n squared entries, so it's big O of n cubed steps. Okay. And again, like integer multiplication, for a long time, people thought this was the best you could do. In fact, people even proved that this is the best you could do. Except the model of computation in which they did it, again, abstraction, right? So the abstraction they used was, well, when you're trying to multiply two matrices, you're trying to add and multiply numbers. So the basic operations you were allowed were additions and multiplications. What else could you possibly want? And they showed that using additions and multiplications, you cannot do it in less than n cubed steps. So you have, that's the best you could do. So let's see if we can do better with divide and conquer. So here's how you might do it. So let's take our matrices and divide them up into A, B, C, D, E, F, G, H. These are now n over 2 by n over 2 matrices. And now the answer is going to look like this. So this matrix on the top left is going to look like A times E plus B times G. So it's as though these were numbers. We take A, first row times first column, A times E plus B times G. This would be first row times second column, A times F plus B times H, C times E plus D times G, etc. Okay, so I just want to make sure you understand that this is actually kosher to do. So let's look at an entry of this matrix and let's see that it turns out right. So let's look at this top left entry. You can do this for any entry, but let's just do top left. So now, what's A times E? Well, so what this is going to be is the top left entry of A times E plus the top left entry of B times E. So what's the top left entry of A times E? Well, you take this row times this column, right? And then what's the top left entry of B times G? You take this row and this column, right? And so when we add them together, it's as though we took this entire row times this entire column. So we are doing exactly the right thing here, right? Is this clear? Okay, so now let's just do, so it's clear. Now what do we have? Well, in order to multiply two n by n matrices, T of n, what do we have to do? We have to do two multiplications for each of these quadrants. So we have to do 8 matrix multiplications. But now these are n over 2 by n over 2 matrices. And then we have to add these matrices together. So we have to do 4 matrix additions. Each matrix addition just requires n squared steps, right? Because we are just multiplying corresponding entries. And if you work this out, you just go look up the master theorem, you'd see T of n is n to the power of log to the base 2, because n goes to n over 2, of 8, because there are 8 subproblems. Log to the base 2 of 8 is 3, so it's n cubed. Right? So we divided, but we didn't, whether we conquered or not is not so clear, right? So, okay. It turns out that, you know, this might seem like we didn't do very much, and this was really not a success at all. But it turns out that, in fact, okay, sorry, you know, that this is actually, in practice, this is a good algorithm. You know, if you really want to multiply matrices, much better to do this divide and conquer, divide and maybe conquer algorithm. It's much better than this row times column. Okay, and the reason again has to do with abstraction. So when we write down that matrix multiplication takes order n cubed steps, what we are assuming is, one, each of these multiplications is a unit step, xik times yk is a unit step, but also we are assuming that accessing these numbers, you know, going into memory and finding each of these numbers is a unit step. So we are assuming we have this RAM abstraction, random access. We have a random access machine. So we have memory where anything we want to look for takes unit time. But of course, we don't have that, right? So there are some things that are sitting in main memory, some things which are sitting in slower memory. And if you have a big matrix, you can't keep all of it in fast memory. And so, you know, so if you look a little deeper into what our machine looks like, in fact, what we want to do is we want to give our caching algorithms as much help as possible. And when you multiply these matrices in this block form, you're actually helping with caching, because you're keeping things together that you want to multiply with each other. Whereas when you multiply row times column, you're just multiplying, you know, you're just everywhere in the matrices. So this is much better. This divide and maybe conquer is much better for caching. And therefore, even though it's order n cubed, it's a better algorithm. Okay, so now how do we actually divide and conquer? Well, the answer is it's not easy. I still don't know why you can divide and conquer. I mean, I can see it, I can work through it, but how did somebody figure it out? I don't know. So we had somebody named, okay, so I put it down over here. There was somebody named Volker Strassen. I believe it was in the 70s. He came up with this remarkable way of you know, of doing you know, multiplying these blocks, you know, doing these 8 multiplications we had, A times E, et cetera, right? So we wanted this first entry to be A times E plus B times G, etc. So we had 8 multiplications. And just as in Karatsuba's algorithm, what Strassen figured out is that if you do these 7 matrix multiplications, and then you do the appropriate kind of additions, subtractions, etc., then you get all of these 4 entries that you want. Okay, so instead of having to do 8 multiplications of n over 2 by n over 2 matrices, we do many more additions and subtractions, but only 7 multiplications. So we end up with T of n equal to 7 T of n over 2 plus order n squared. Now the order has a bigger constant associated with it. But remember, our recurrence relation doesn't mind that, because it's still, T of n is still dominated by this n to the power of log to the base 2 of 7. Okay. So that's 2.7 something. You know, it's a better algorithm. So after Strassen, there were, there was a sequence of improvements by Strassen and others, which improved this matrix multiplication exponent by finding actually more and more, this was an ad hoc way of finding these this way of multiplying the matrices. But it turns out there's now a big theory around it, and the best people know how to do is something like n to the 2.31. Okay, so this is Winograd, right? Coppersmith and Winograd, and people believe that in fact the correct answer. So the belief is that we should have something which is approximately n squared, right? So that matrix multiplication should eventually become something like n squared. And maybe even with an algorithm that might turn out to be very simple, but this is sort of a big open question that people have been grinding away at. Okay, so let me stop here and see if there are any questions.
I wanted to very quickly ask about the RAM management thing you mentioned before, and how you can load parts of the matrices into your cache at a time. I'm still unsure as to how that's actually making the process faster, because for example, for the submatrix A, you have to load it for 2 of the quadrants, and that applies for all 8 of the submatrices.
So here's what I mean. So if you're trying to multiply x times y, what it says is you should multiply a times e, right? And then you can multiply b times f. So if you have a and if your cache is large enough to hold a and e, then you can just multiply them together. It's very fast, right? But now, let's suppose it's not. What will your algorithm do? Well, in order to multiply a times e, it'll break them up into 4 pieces each. And now I'll take this first part of A, let's call it A naught, and the first part of E, call it E naught. These are now much smaller matrices. It'll be trying to multiply them together. Now that might be, those might be small enough that they are held in your cache directly. And so you'll just whiz through the, just go ahead and multiply them instead of having to pick through a row and a column and then another row and a column. So it's now much less, it's much less localized. So now you're just homing in on these localized pieces, which you're now multiplying with each other. Eventually, at the bottom of the recursion, you will just do standard matrix multiplication. So when the matrices are small enough, you might just go ahead and multiply row times column, and that might be fast enough.
Thank you.
Yeah, sure.
Could you briefly repeat where those 7 terms come from that we multiply?
Where do they come from? Okay, so remember, X consisted of these 4 submatrices. These are n by 2 by n by 2, A, B, C, D. Y is E, F, G, H. So now what you do is you compute A times F minus H. A plus B times H. Call these P1, P2, P3, P4, etc. So these are all, A is an n over 2 by n over 2 matrix. F minus H is also an n over 2 by n over 2 matrix. Right, so you go ahead and do these 7 multiplications of n over 2 by n over 2 matrices. So you get 7 matrices which are n over 2 by n over 2, P1, P2, P3 up to P7. Now, the top left entry, this quadrant is going to be P4 plus P5 minus P2 plus P6. Okay, so and if you compute it, lo and behold, it'll turn out to be A times E plus B times G, which is what it should have been. Right, so now what did we do here? We did these 7, we did lots of additions to figure out A plus D, E plus H, etc., etc. Then we did these 7 multiplications of n over 2 by n over 2 matrices. Then we did some more additions and subtractions to get P4 plus P5 minus P2 plus P6, etc. And lo and behold, we had the four different submatrices that we wanted in our answer, right? So that's why we had 7 multiplications of n over 2 matrices. lots of additions, which were order n squared, and that's how we got the running time.
I guess I was mainly confused about like where the additions themselves come from. Is it just like factoring the different things that we end up seeing when we multiply it normally?
Yeah, so how you're saying, how did Strassen figure these out?
Okay.
Yeah, and I don't know.
Okay.
Nobody knows.
Yeah.
Professor,
Yeah. Yes.
How would you go about proving that it's not possible to reduce this into 6 subdivisions?
You know, I think that it's actually true that it cannot be reduced to 6 multiplications. But what you could do is, instead of breaking up into 2 by 2, right? You broke x into 4 blocks, right? 2 by 2 blocks. You could break it up into 3 by 3 or 4 by 4, and then reduce the number of multiplications. And so this is how you get down to n to the 2.31. And the question is, can you reduce it? You know, can you break it up into, you know, k by k for some constant k, and then do it in many fewer than whatever it is, you know, k cubed multiplications, and you know, in such a way that you would reduce this exponent. So that's the whole, you know, that's the matrix multiplication challenge.
Maybe one thing about this, how to prove that you require at least 7. So it turns out you can talk about this problem. It's called the tensor rank of matrix multiplication. It turns out to be an NP hard question, and we will talk about NP hardness later in the course. So it's not an easy question to solve, but you know, this is sort of finite setting where we are talking about like 2 by 2 matrices. So it can be solved, but in general, it would take time that sort of grows probably exponential with the size of the matrix, like just to determine how many multiplication you need.
Yeah.
Professor.
Yeah, go ahead. Sorry.
Yeah, sure. I have one last question. So previously, when we were talking about multiplication, we were talking about 2 n-bit numbers. So when we multiply 2 n-bit numbers, we were getting like n square complexity. But over here, we're also multiplying numbers, right? But why do we consider as like we consider O n as time complexity?
Yeah. So very, very good question. That's another place where we are abstracting. So now that we are multiplying matrices, we are sort of thinking, you know, multiplying numbers, that's good stuff. So we are just saying multiplying 2 numbers is a unit step operation. So we are no longer thinking that the entries of these matrices are very large numbers. You know, maybe they are small numbers where, you know, at most 32 bits or at most 64 bits. So you can just use your, you know, so you have built-in, you know, your built-in library will just multiply them in unit step, right? These are your instructions on your machine. So multiplying the numbers themselves, we are saying is easy, but now since you have matrices, you have to multiply lots of numbers with each other and add and so on. And so we are saying that takes n cubed time. Then you reduce that number.
Okay. Thank you, Professor.
Sure. More questions?
I had a quick question about whether abstraction tends to help with algorithms in general. Because when you're talking about, I know in general, like abstraction helps with improving the runtime algorithms, but with the divide and conquer, it helped even though it didn't actually change the upper bound. So, in those cases where abstraction would help, is it just because of different ways you can parallelize the computations?
Well, no. So here's the way to think about it, right? So, you know, computers and programs, these are complicated things, right? These are complicated. So we need to have a model to simplify them so that we can think about them. And so, you know, so when we analyze algorithms, you know, even when you're writing a program, you implicitly have a model in mind, right? And you know, the only question is the model that you have in mind appropriate for the program that you're writing, or there a mismatch? And and so what we do when we design algorithms is we sort of place ourselves, we sort of look at the computer and we say, well, look, it's what it is. We understand that there are many more complications than we are taking into account. But for the purpose of these problems that we have, we are going to abstract away some of the complications and say these are the main things that matter to us, that should matter. And then we design the algorithm, we analyze it, and then at some point we might realize we threw away too much. Maybe, so for instance, with matrix multiplication, we might realize at some point, look, our matrices are large. They don't, this order one retrieval time, this was simplifying things a bit too much. And so maybe we want to put that back in again. And so, then there are ways of doing that explicitly. So there are these hierarchical memory models which you can then analyze the algorithm in, and people do that, right? Depending upon at what level you want to design algorithms, sometimes you want to throw away all these complications and just think about the algorithms in the simplest model, and then just say, look, here's how it works. That's the highest order term. But then you always have to unwind it, and you have to say, okay, but is there there's a next level at which you should study it, where you now open up some of the can of worms, and you say, well, I'll just open it up just a little bit more and now understand the algorithms. Or when you actually go to program it, then you want to open up the can of worms even further and say, well, there are these further complications, so let me find my way through more pragmatically, using what I know from algorithms as a guidepost, to find my way through. So that's how you should be thinking about it.
That makes sense. So levels of abstraction, and then when programming it, there's levels of memory abstraction.
Yeah.
Thank you.
Yeah, sure. Thank you.
Let me stop the recording.
Mm-hmm.